Alright, welcome everybody. So today we're going to talk to you about, or I'm going to talk to you about atomic radius and the trends. And so in the last video I quickly defined atomic radius as the distance between the nucleus and the valence electrons. So how does this change as we go across a group, across a period, or down a group? So when we go down a group, our radius is increasing. And when we go across a period, our radius is decreasing. Now going down a group, when we think about the terms that define an atom, the atomic structure terms, when we ask, why does this increase going down a group? Well, it mainly has to do with this increased number of energy levels and an increased shielding. So if I were to give you an explanation as to why the radius increases down a group, you have more principal energy levels. So the electrons repel each other and they move further from the positive nucleus. So, if you were to ask me, well, hey, why does this radius increase? It will mainly be due to those increase in principal energy levels. Now, it's important to note here, and we'll get into this when we talk about ionization energy, that the attraction between that electron, that outer valence electron, is going to be less when you look at how well it's attracted to the nucleus. Now, when we go across, the radius decreases, and this explanation is a little bit more difficult. When you go across, remember, in a period you have the same number of principal energy levels, pels, but you have an increased number of protons, which are positive. The nuclear charge goes up. So now this increased Zeph, because really you're keeping the same number of inner electrons and increasing the number of protons, so an increase in the Zeph will cause a greater attraction between the nucleus and the electrons, and it'll pull them in closer. So the electrons are pulled in closer. And so that causes you to have a lower or smaller radius that occurs. So, these are the trends going down and going across. If we look at, the atomic radii going down in black here, we have lithium, sodium, potassium. You see they're getting larger. You could do that for F and chlorine and bromine and see that they're getting larger because they're adding more energy levels. If we were to go across, and show what that looks like across for the atom, we would have lithium, then we'd have beryllium, and then boron, and then oxygen, and then fluorine. Now notice that they also show the ionic radii, and when you become a positive ion, if we were to look at beryllium, for example, if you become a positive ion, you're losing electrons, and you're really losing an entire shell of electrons, and so your atom gets smaller. And so that's a general trend that we see when you become a positive ion, you are smaller than your atomic radius, or smaller than your atom, I should just say. And if you are a negative ion, you're going to become larger than the atom. And you can see that with the negative ones here. If we look at oxygen and O2, the O2 has gained those 2 electrons, and it becomes quite a bit larger than what the oxygen was. Now, there's something important that I don't know was mentioned last year or not, but it's called an Isoelectronic Series. It's really hard to compare 2 different, species when you have one that has more protons than the other and they don't have the same number of electrons. And so an isoelectronic series tends to, or tries to, address that. And so this would be an example of an isoelectronic series around neon. Neon has 10 electrons, and it has 10 protons. It's an atom. But now if I were to go and take and look at F minus also has 10 electrons, but 9 protons. O2 minus has 10 electrons, but 8 protons. And we could even go the other way. I could keep going with the negative ones, but I can make some positive ones here too. Na plus would be 10 electrons and 11 protons. And magnesium plus 2, that one would be 10 electrons and 12 protons. And so you can see all of these species here, they have the same number of electrons that makes them isoelectronic. And so isoelectronic has the same number of electrons. But what's nice about this isoelectronic series is that it makes it really easy to compare their relative radii. And so something that has 8 protons has a lower Zeph. And so it has a higher radius, a bigger radius. Compared to something that's magnesium plus 2, now it's lost those 2 electrons. It has a higher Zeph. And so those 12 protons pull on those electrons more, it would have a smaller radius. Okay, so let's move on to ionization energy. Ionization energy, when you go down a group, remember this is the energy to lose an electron, the ionization energy will decrease. And when you go across a period, the ionization energy generally increases, but we'll talk about the exceptions. So why does the ionization energy decrease? Well, the electrons, the valence electrons, are further away. They're more shielded from the nucleus. That equals lower attraction, and that means that you need less energy to remove it. If we go across, well, now the valence electrons, they are closer to the nucleus. There's also a greater Zeph pulling on those electrons. That means that the attraction is greater. And so that will equal a higher amount of energy to remove an electron. So the ionization energy goes up. So these are the general trends. Going down, the trend stays true. Going across, there's some blips we need to talk about. And so here, this shows you, like going across a period, we have a general trend where we go up. But there's some blips along the way, like nitrogen and oxygen and beryllium and boron. And we see that if you look at the next period, we have the same type of thing, a general trend up, but then some blips going down. And you don't even really see it so much with phosphorus and sulfur, but you definitely see it again with magnesium and aluminum. And so why is that the case? Well, with beryllium and boron, what's happening is beryllium, if we look at this, it has 4 protons, and boron has 5 protons. Boron has a higher Zeph. But when you look at the electron configuration, 1s2, 2s2, it's these electrons, the 2s2, that are lost. Whereas in boron, 1s2, 2s2, 2p1, it's these 2p electrons that are lost. And what's happening basically is that these 2p, they're a little bit more shielded. That will equal less attraction. And that will equal lower ionization energy. The other exception was nitrogen and oxygen. And again, nitrogen has 7 protons, oxygen has 8 protons. Oxygen should be able to, hold on to its electrons more. But then when I look at this, I see that, oh yeah, this one is 1s2, 2s2, 2p3, 1s2, 2s2, 2p4. They're both in p, so what's going on here? Well, if I go even deeper and I draw out the orbitals with the electrons, for 2p they're unpaired. When it's 2p3, when it's 2p4, we have to pair up the electrons. This pairing is what causes the lower ionization energy. You have a higher electron repulsion. That will lead to a decreased attraction to the nucleus. and that will lead to a lower ionization energy. Now, a question I ask you, and some people ask me this question, is, well, why doesn't fluorine then have a lower one? So maybe you could come up with an explanation. Why is fluorine higher? Why is neon higher than fluorine? Why does it go up? Why is it only that one blip there? Let's see what you come up with. All right, the last thing I want to quickly talk to you about is the successive ionization energies. So, we always talk about the first ionization energy going across here. This is for the group period 3 elements. And we see, that the ionization energy generally does go up for them. But what happens when I look at the second ionization energy, the third, the fourth? What I notice is that there's a big jump between sodium's first and sodium's second ionization energy. Why is that? Well, sodium has one valence electron, 1s2, 2s2, 2p6, 3s1. Removing the first electron will remove it from 3s1. And now we'll have Na plus here. Now, if I want to go to 1s2, 2s2, 2p5 and make it Na plus 2, well, now I'm removing a core electron. The Zeph on that electron is much higher. The attraction that electron has for the nucleus is much higher. It's much more difficult to remove. And you see that with the successive ionization energies. Magnesium has 2 valence electrons. So removing the first, okay. Removing the second is more difficult. Removing the third, though, look at the huge jump here. Removing the third, because now we're in the core electrons. We go to aluminum, first 3 easy, 3 valence electrons, go into the core, much more difficult. And so, this just kind of gives you an idea of, how many valence electrons there are. You should actually be able to see that jump. Now, how do they actually do this? How do they measure the amount of energy required? That's what we're going to talk about next time. It's called photoelectron spectroscopy. All right. I will see you next time. Thanks so much.